Okay, in this video I want to show how to create a fullness forecasting model. So let's start by having a look at the data that we have to build this model. So we have basically two files here. This one has all the precipitation data from 4 different stations in the watershed that we are analyzing. As you can see, the time series go from 2003 to 2014. And then we have this other file that has also a time series with the inflow into the Batangai Dam. And the time series is pretty much the same, so they overlap a lot. Well, this one is a little shorter, I think. But, well, that really doesn't matter. In fullness, you don't need to provide the exact same length for the time series. It will just match the data that it will find. So now we're going to open this tool that we developed with the help of the World Bank to implement fullness methods. And we're going to start by adding this time series. So let's start with the precipitation. I don't think that we have no data, but just in case, this is the value I usually use. So now it loaded the 4 time series with the independent variables. And now we're going to add the inflow data as well. Again. And well, we have a conflict here because that name in the column is already used by one of the stations. So let's just call it inflow, and that will do. So now we have to tell fullness which is the dependent variable. So we come here, we select the time series, and we click dependent here, and that's it. Now we have our model. It's ready to be used. So let's test it. So let's say that we have a forecast of 5 millimeters of precipitation in each of these 4 stations, and when I run the model, well, there I got all the results. So let's take a look at what these results show. First, we have 4 different methods here, actually, to calculate a flow, to forecast a flow based on this forecast precipitation. This first one uses all the records in the time series and performs an inverse distance weighted interpolation using all of them. So the ones that are closest to these values will have more weight than the others that are different. Then we have this closest actually goes and picks the most similar situation or scenario in the past in the record. And then these 5 ones have to do with with an ensemble. Fullness will select a number of the most similar scenarios and will calculate the statistics from them. So we can see that it found values with a range from 218 to 39, so it's quite broad, and well, it has quite large standard deviation. And the final method is a method that calculates a probability of exceedance of a certain threshold. So now the threshold is by default is 0, so let's change that. Let's put a threshold of 400 cubic meters per second. And now if we run it again, well, it says that we have a very, very low probability of exceeding that value with this precipitation. I can also click here, and when I run the model, it will display the box and whiskers with all the values in the ensemble. So we can see that we're pretty much below the threshold. Let's try I don't know, let's say that we are expecting a big storm, so 50 millimeters in each of the stations. We run the model, and this is the results that we get. So apparently in our boxes whiskers or an ensemble, we seem to be above and quite high above the threshold that we set it, but nevertheless this last model actually says 7.4. So this gives an indication that the model is not working very good. We can see, for instance, that the inverse distance weighted is below, and the closest also is below the threshold, but then the median and the mean are higher. So this brings us to a question, okay, how good is our model? So one thing I forgot to mention is that here we can see all the scenarios in the past that are actually similar to this one. So the closest one actually occurred in 2006 on February, and we found this value, so 46, 60, 56, and 49. So this is the closest event in the past where this was pretty much the values that we are forecasting. And the observed inflow that day was 290. But then we have this other one here, and well, we won't get into details now, but this is not a real observed scenario. It's an extrapolated one, because one of the characteristics of FUNES is that it allows us to use some imagination of what would happen if we had values that we'd never observed before. So this gives me an indication that we are having some problems with the extrapolation. Probably the values that we're using are not very accurate, because this one that says extrapolation factor 1, again we have 228, so we're probably have a problem with extrapolation. That could be, we could just extrapolate, turn the extrapolation off directly by putting a 0 here and run it again, and well, this looks much better. So one thing that we should try to improve in our model is this extrapolation method. So in this first video, what I wanted to show is how easy it takes about 20 seconds to set a model and to get our results. But in the next video, we're going to see or find ways using the same tool to assess how good our model is. And then in other videos, we're going to explore ways to improve this model.